A couple of things before we get started. I'm sure y'all are aware that Monday, Amazon had something going on, that anything that was electronic or any kind of software that was used by the Amazon system was down. I had no idea Canvas was part of Amazon. I learned something. So everything I said that I was going to do on Monday, I couldn't do until Tuesday. That's number one. Number two is that the audio for the second half of Monday's lecture didn't record. I found out, number two,
I was wondering why it's like 34 minutes, okay.
that if this right here is plugged in, it doesn't record.
Oh.
I tested it out in my office, but I had my, I didn't have 100% battery, so I had to plug in, and so I thought, well, I'll just use that. Well, it doesn't record. So I'm gonna have to voice over everything that was in the second hour, so I'll try to get that done today. I also finished up the review for positioning, so that's available in Canvas as well. So what we're doing today is it's going to be kind of a lengthy review over the material that I recorded, and I posted a different lecture or tagged a different lecture in the notes of the lecture over Friday's material. So the first part of chapter 5, and it's a little bit more comprehensive than the one I recorded for Friday of last week. So a little bit of a lengthy review of electrostatics and electrodynamics. And so what we're going to do today is we're going to go through magnetism. Hopefully we'll get all the way through magnetism. And then on, what is today? Wednesday, Friday, we'll get into electromagnetism. So this chapter is electricity, magnetism, and then we'll get into electromagnetism, which is using electricity to create magnetism. So what Friday's lecture was about was electricity and what it means to be electrified, and that is to have too many or too few negative charges. And I say it that way because that's really what we're focusing on is the negative charge, right? So it can be positively charged and be electrified. It can be negatively charged and be electrified. But fundamentally what we're talking about is too many or too few electrons. We can't really move the protons, so we're talking about electrons when we're talking about electricity. But we can't move the protons because protons are in the nucleus, and if we move the nucleus, essentially we're moving the conductor, right? So I mentioned that before. So we're always talking about when we're talking about electricity, we're talking about electrons. So the electrons are easy to move, they're outside the nucleus, and for the reasons that we'll talk about in a minute, they move along quite easily. So electrostatics is a study of static electricity, and if you saw the video, you saw where I posted a couple of videos about static electricity and how it can be very dangerous at the gas pump. So electrostatics is stationary electric charges, and I talked about how it is that you can build up that static electric charge, and that would be through friction, contact, and induction, or how those, not necessarily build them up, but how you can manipulate those electric charges. So wintertime, you walk across a carpet, you scoop up electrons, slide across the seat in your car, you pick up electrons, and you are electrified at that point. It's an important distinction to note that what we're not talking about here is electrocution. That's something totally different. Somebody gets shocked and they say, well, I got electrocuted. You, in fact, did not, because you would not be talking to me if you got electrocuted. Electrocution means you are dead. So electrocution and being shocked are two totally different things. Electrocution is fatal. So you're electrified by picking up those electrons, and then you distribute those either by contact or induction. So they go back into the ground, back into the car, or wherever. So that's contact and induction. So what I did not mention is electric ground. So what you have with electricity is, you're moving electrons. The net electric charge of the universe is neutral. So we don't create electrons, we just move them around, we bounce them around. So the net electric charge is neutral, and if you've ever worked with electricity, you know that for circuits to be complete, somewhere along the line of circuitry there has to be a ground. Okay, so if you follow, pop the hood on your car, you follow the electric lines out, chances are you're going to find one of the lines coming off of the negative post on your battery, and I'll talk about that here in a minute. Negative post on your battery goes to the frame of your car or fender well or something like that. So that's the grounding point. So I'll talk about that here in a bit too. So an example of an electric ground is the earth, and an electric ground is just a place that can accept electrons. It's kind of like a storehouse for electrons. So electrostatic force got into that, and that is the force of attraction or repulsion between electrostatic charges. So when you're thinking about electrostatic charges, again, we're talking about electrons. And the electrostatic laws, there are four parts, or four electrostatic charges, or electrostatic laws, and that is like charges repel and unlike charges attract, right? So you've heard opposites attract all your life, right? And that applies to electrons, doesn't really apply to people, and relationships. This is just your dad lecture. Opposites attract for a while. Right? Find somebody who's a little bit more like you. Opposites attract for a little while, and then you just get irritated with each other, and it's going to end badly. So with electrons, opposites attract, or with electric charges, opposites attract, and like charges repel. And then we get to distribution, and I use water as an illustration quite a bit in discussions of electricity. Distribution is that it's going to distribute evenly throughout a conductor, and a conductor is something that allows electrons to flow pretty evenly. So in the example, you take a cup of water and you pour it on the floor, and oddly enough, I did not bring my water. You pour the water on the floor, and what happens to the water? It just stacks up, right? Not unless it's snow. It spreads out. So it finds its own level, and electricity is the same way. So if we have a wire and we supply electrons to it, then the electrons will evenly distribute along the face of the conductor. Because they're all negative charge, they're going to push each other apart until a point where, they have, let's say our wire has a roadblock here and a roadblock there. They're going to push each other apart to a point where they're evenly spaced. So it's, because they're all negative charge, they're going to push each other apart until they find their own level. So, but if you bend that wire, kind of use this as an illustration, is if you've got electrons, if you bend that wire, then the bottom side of this wire becomes more sharp. The electrons get mashed together. The electrons on the top kind of spread out more. And so on a wire that's bent, then they tend to congregate. They tend to compress. They get closer together. Okay, where you're actually going to see this happen is in surgery. Okay, so in surgery, what you're going to see, just pay attention to everybody in surgery. So the anesthesiologists actually use a miniature stun gun to test, especially in neuro cases, to see whether or not the patient they'll give them a paralytic to see whether or not the patient is truly paralyzed. And so, just like radiation, medicine has a half-life. So they inject you and you're paralyzed for a time being, for a time, and then it starts to wear off over time. So let's say you got a 4-hour neuro case, they're gonna have to give you more medicine. They're not just gonna give you a dose right up front, you're gonna be asleep for 4 hours. They're gonna have to continue to give you more medicine. So what they'll do is they'll take this little stun gun, I don't even know what they call it, a neurostimulator or something, but it's a little bitty thing, and it's just got a couple of buttons on it. It's got 2 things sticking off of it with 2 round points on the end of it. Sharpest curvature, right? That's not curved, right? Sharpest curvature. So when they push the button, then what happens is electrons go towards the end of this. There's a little miniature transformer in this thing. The electrons go to the end of this, and they congregate on the end of this thing, all right? So you got electrons all over this thing, and what they'll do is they'll put it right on the patient. Makes me laugh every single time. But they put it right on the patient's temple, and they electrify it. All right, so they push the button, they put this thing on their temple, and they electrify it. And if they get any kind of reaction, they know that the patient is not paralyzed. Well, what kind of reaction are you talking about? Well, they're sitting there, and then and the neck doesn't move, but I can't hardly do that without, moving my neck. But that side of their face will scrunch up. And they say, okay, well, he needs more medicine, and they'll inject more medicine, make him paralyzed again. Okay? So sharpest curvature, even distribution, but then concentrates on the sharpest curvature. Basis for any kind of stun gun, or if you were raised on a farm or whatever, cattle prod, same thing. It does the exact same thing. Okay, so like charges repel, unlike charges attract. They distribute evenly unless you got a sharp curvature. And the last one is really what we refer to as Coulomb's law, and it's got two parts to it. So Coulomb's law says that the electrostatic force is equivalent to basically the quantity of electrostatic charges you have. So we've got, in this case, we got 9 electrostatic charges. So our electrostatic charge would be, in this case, just throwing numbers, 9. So if I added more of them, then what would it be? It'd be equivalent to however many more I added, right? So the more you have, the more you have, right? So the more electrostatic charges you have, the product of those electrostatic charges, the more electrostatic charge you have. But what if now I take this, my roadblocks, I get them out of the way, and I extend these way out here? What's going to happen to my electrons because of distribution? They're going to spread out. Now how much charge do you have? You still have the same number, but is it going to be as significant? No. And the answer is no. Okay? So Coulomb's law says the more you have, the more you have, but it's going to be inversely proportional to the square of the distance between them, which sounds exactly like the inverse square law. It is just the inverse square law. Okay? So those are your 4 laws of electrostatics. We're going to look at Coulomb's law again whenever we get into magnetism here in a bit. So then we've got electric potential. Electric potential is potential difference between one end of a conductor and the other end of a conductor. And it's basically, again, in the water analogy, it's the force behind the movement of the electrons. So it's kind of like you turn the water on, you've got so much water coming out, and if you want to increase how much water is coming out, you got to add more pressure. Right? So it's the force behind, it's the pressure behind the movement of the electrons. We'll kind of talk about that again here in a minute when we get into electrodynamics. So, and we'll look at Ohm's law. So electric potential is potential difference between one end and the other end. In the X-ray tube, it's a potential difference between the cathode and the anode, and it's how fast we're going to move those electrons across the tube. Okay, and we measure that in kVp. So as kVp goes up, the pressure on those electrons travel across the tube increases. Sends the electrons across the tube faster. As they go across the tube faster, they carry what kind of energy with them? Energy of motion is kinetic energy, right? So it's potential energy, potential difference between the two that drives the kinetic energy. The more kinetic energy it has, the more energy it has to lose. So what are our 2 ways of creating X-rays? We got characteristic, which plays a part here, but the other one is brim. So how do we create brims? Slowing down. We lose that kinetic energy, so the more kinetic energy we have, the more kinetic energy we have to lose, and therefore we get higher kVp X-ray photons. Okay? In that way, kVp controls, in the X-ray tube, the potential difference between cathode and anode, the speed of the electrons, and in the X-ray beam, it controls the energy of the X-ray beam. So what's the significance of that? Well, what does kVp control in the patient? Penetration, right. So the higher the kVp, the higher potential difference, the higher the kinetic energy, because the faster the electrons, so that we create higher energy X-ray photons that are more likely to penetrate through the patient. right? So stuff's starting to tie together, right? All this stuff that we talked about already wasn't just, just to talk about. Not saying that that's what you thought, but, just kind of, trying to help to identify that. All right, so then we get into electrodynamics, and that's moving electric charges. We have to have something for them to move on, and that will be a conductor, right? So a conductor allows electrons to flow easily, not to be confused with a superconductor. A superconductor is a conductor. It's just a more efficient conductor. And you have to have special conditions for a superconductor to truly be a superconductor. We have to remove resistance inherent in the wire. So what I mean by that is those electrons, even though we're on a conductor and a conductor allows electrons to flow, anytime we send electrons through a wire, we're going to create two things. We'll talk about one of them on Friday, but the other one is heat. It's just friction, right? Even though these are tiny, they're tiny balls of matter, and anytime you have matter running against matter, you've got friction, and friction's going to create heat, right? So in order for a conductor to be truly efficient, you want to, as efficient as it could possibly be, you want to remove some of that resistance. So with the resistance creating heat, if we remove the heat, then we will remove some of the resistance. All right, so have you ever tried to use your computer in a hot room or outside on a hot day? How well does it work? Not as well as if you're in the house because it's hot, right? Try to charge your phone in the car, or you leave your phone in the car hooked up to the charger, you come back and you crank the car up. What's your phone say? Yeah, I'll get to that charging thing after this thing cools down some, right? So kind of the same thing. So a superconductor is a conductor. It's a very good conductor. It may not be the same type of conducting material that we use in everyday life, like copper, but it's got to be kept really cold. So that's conductor and superconductor. Insulator is something that keeps those in there. So, we got a electric thing here. If we could see the wire, then we have the potential for what we refer to as a short circuit, right? So we have to keep the electrons flowing where we want the electrons to go, and that's what an insulator does, okay? So sometimes you can see the wires, and I relate this story sometimes. I'll try to run through it real quick. Electric fences. Anybody ever dealt with electric fence? Okay, so you actually see the wire in an electric fence. You want to be able to see the wire because, whatever you want to stay away from the electric fence, you want them to get shocked a time or two. It's very high voltage, very low amperage, so it hurts, but it's not harmful, all right? You know the difference. I mean, you pinch yourself, it hurts, right? Is it harmful? Oh, you're fine, right? Well, kind of the same thing with an electric fence. So with an electric fence, what you have is an electric fence generator with wires coming out of it, and it's also, it's plugged into a electric ground as well. So with an electric fence, what you've got is a complete circuit with exposed wires. The problem with the electric fence is that if anything touches it, you get what you refer to as short circuit, and it nullifies the whole thing, okay? So, if a blade of grass gets on it, well, you cut fresh grass, how's the grass feel? Wet. It's wet, right? That means it's full of water. And if you watch the video, I said water is a good conductor, providing it's pure water. Is the water pure in grass? No, it's not. It's wet and it's water, but it's not pure water, right? So that water is going to conduct that electricity into the ground wherever the grass is touching it. Okay. Now you want to see how stupid I am? This is a story. I've got goats, and this is the second time I've had goats. And so goats, if you've never been around, anybody been around goats? Okay. So you can back me up on this. Anybody who said, whoever it is came up with saying that curiosity killed a cat never met the goat. Okay. If they can get into something, they're going to get into something. If they can get out, they're going to get out. So the house that I was originally living in had a long back porch that the goats like to get on, but anywhere a goat gets, it poops. So you don't want the goat on your porch, right? So I put an electric fence around the porch, and I got out there one day, and I just wasn't thinking about it. I'd plug it in, and this is awful, but I'd grab one of the goats and I'd pull him into it. So he would feel it. I would feel it too, full disclosure, it hit me just as hard as it hit him, but he thought he was gonna die. I knew, it's just high voltage, low amperage. I let him go, and it goes to stay away from it, and so I'd unplug the generator. And then, a couple of weeks would go by, and they'd be back on the porch. So we'd do it all over again. So I plugged the generator in, and I walked by. I'm also cheap. You can buy an electric fence tester for under $10. Not gonna do it. Not gonna do it. Why? Because I can detect electricity, right? All I gotta do is touch the wire. It's exposed wire. It doesn't have any insulation on it. So I touch the wire, I get nothing. And I touch and hold the wire. I can vaguely feel a tingle. There's still nothing. So I'm thinking, okay, I got some grass that's growing up on it. So I walk all the way around, and I'm looking, I'm pulling up grass. Reach over and touch it again, still nothing. Okay, what is an insulator? Stops the flow of electricity, right. So stops the flow of electricity. What were examples of, if you watch the video, what were examples? Rubber, right. Let this set on you for just a minute. I'm outside on a porch, walking around, there's goat poop everywhere. You think I'm barefoot? What am I wearing? Shoes, right. So look at the bottom of your shoes. What's on the bottom of the shoes? Rubber, right. So I'm not grounded, right? But now I got to get down on my hands and knees because I'm thinking I got some grass. I'm down on my hands and knees. I'm crawling around looking for the grass that is not touching the wire, but I do. I got both hands and both hands and both knees on the ground, and I get blasted. Right? So, duh, the funniest part of this story. I know I'm taking up some time here, but the funniest part of the story is. Probably 4 years ago, my oldest son, that son, that I've, told you, tried to amputate a thumb and a couple of fingers, he calls me up and he says, Dad, my dog's getting out and my electric fence isn't working. So I'll go around, pull up all the weeds. He said, okay. So he does. He calls me up. He says, it's still not working. I said, did the dogs get close to it? He said, no, but it's not working. They're going to get out. I said, the electric fence is working. He said, it's not working. I touched it, and it's not working. I said, what's on your feet? He said, shoes. I said, okay, your electric fence is working. He said, he's kind of like me. He's a hard learner. Nothing comes easy to this kid. I said, okay. He's arguing with me. I said, it's working. Your shoes are preventing you from feeling the shock. He said, nah, I don't think so. I said, I tell you what, reach over and grab the metal fence, and then grab the wire. And I screamed this. Really the funniest part of this story is my younger son was sitting there, and I had him on speakerphone, and the yell his brother let out was just glorious. And if you all happen to be a younger sibling, you can really, really appreciate that. Hearing your older sibling, especially your older brother, scream like a little girl, it's hilarious. So anyway, insulators, would prevent that. So if I've got insulation all the way around that, well, the electric fence wouldn't be any good for keeping goats off my porch, but it would be good for preventing short circuits and from preventing me from, being shocked. So we've got we've got insulators, we've got conductors, superconductors, and we've got semiconductors. And usually that's silicone. What we'll have is pure silicone and silicone with and we'll get into this later in the semester, but silicone with a contaminant in it, kind of stuck together. So electrons will go in one direction, won't go in the opposite direction. I'll tell you later in the semester how those work and where we use those. All right, so then let's see, another thing that we didn't really talk about was Ohm's law. We talked about the different types of circuit, parallel and series circuits. Yeah, thank you. I didn't really talk about Ohm's law, but Ohm's law is just a mathematical equation, V equals IR. Okay, so when voltage is constant, then intensity, which is I, and R is resistance, are inversely proportional. So again, simplifying the equation, we've got 1 equals 1 times 1, right? But if 1 doesn't change and I increase, let's say, my intensity to 2, then what has to happen with my resistance in order to accomplish that? It's got to decrease, right? So it's got to go down to 1/2 to keep it mathematically sound. Now, if, though, I wanted to keep my resistance the same, what would naturally have to happen to my voltage in order to get that kind of current flow intensity? Well, what does that say? 2 times 1 is 1? Is it? No. Then 2 times 1 would have to equal 2. Okay, so back to water. All right, so back to water. If V equals the pressure of the water, you can kind of see how this works, right? You want twice the flow of water and you've got the same size water hose. What do you have to do to get that much water through that same water hose? More water pressure, right? Okay, so that's Ohm's law in a kind of a quick nutshell. All right, so we have two different types of current. We got direct current, alternating current, and we talked about that earlier in the semester. Direct current is current that just goes in one direction, and alternating current kind of goes back and forth. And we're going to use both of those. We're going to use alternating current, and we'll talk about this on Friday. We're going to use alternating current up to a point in the circuit, and then we have to change it from alternating current to direct current for reasons I'll talk about later again in the semester. And while I'm thinking about it, resistance. We can change resistance in a lot of different ways. So we can change the type of wire, right? So we go from copper to aluminum. Copper is more efficient. Aluminum, you may burn aluminum up. You know, they used aluminum in wiring houses for a while, and they had a problem with fires, so they stopped doing that. So you've got aluminum versus copper, so some conductors more efficient than others. The longer a wire is, the more resistance there is. And that's just kind of common sense. If an electron only has to stagger down a wire that's that long, it's only going to create so much heat, right? But if it goes down one that's much longer, then it's going to create more, right? So the heat equals resistance in this case. Does that make sense? Mm-hmm. Also, back to the water analogy, you know, when we talked about this as well, is if you've got a very small hose, how much water can you put through it? Not a lot. You've got a lot of resistance. As opposed to a pipe, how much resistance is in that pipe? Not much. So you can change the diameter of the wire, you can change the length of the wire, you can change the properties of the wire, and you can also put into the wire different types of resistors. I used in the video the example of Christmas lights and things like that, right? So when we're talking about resistance, we're talking about the resistance inherent in the circuit. When we're talking about a resistor, that is something inside of the circuit that we're using, like a light bulb or something like that. So you can add a resistor, change the diameter of the wire, change the length of the wire, change the top of the wire. So any questions on all that? Holy smokes, that was a long review. How long was that? 30-minute review before we get into the new material. Any questions? Well, then magnetism, a few things about magnetism. There's a lot of similarities between magnetism and electricity. You know, what we're talking about is electromagnetic energy, right? So properties are pretty shared. So just some general information. Lodestone is a natural magnet. There are two different types of magnets from two different perspectives. One is natural magnet, one is man-made magnet. Okay? So within those, we've also got what we refer to as permanent magnets and temporary magnets. To simplify temporary magnets, most of the time when we're talking about temporary magnets, that's magnetism that you can turn off with a flip of a switch. Okay? So that's most of the time. You flip a switch to turn it off. So when we send electricity through a circuit, down a wire, we're going to create two things. One we've already talked about, and that's heat. And the other is, we've also talked about in the opening lecture for this semester, and that is magnetism. All right, so we send any charged particle in motion creates magnetism. So we got a magnetic field anytime we send electrons through a circuit. Okay? So if we turn the light switch on, we create magnetism. We turn the light switch off, it goes away. All right, so that's a temporary magnet. It's not permanent. So we'll get a little bit deeper into that here in a minute. Some other basic things about magnetism is that, okay, first off, if you've read through the chapter, I told you before that Bushong is kind of a character, right? So down at the bottom of page 77, you know, one theory behind the discovery of magnetism was that Roman troops were walking across a specific area and they would find metal shavings on the bottom of their sandals, which were nailed together, right? So something was sticking to it, and that was natural magnetism. And the theory is that it was discovered in a village, I think in Turkey, called Magnesia. All right, so if you look at the bottom of the page, 77, it says, if you walk around the North Pole from any spot on Earth, you will find water. Anyway, magnetism comes from the name of the ancient village where the cows were very ancient also. When milked, they produced milk of magnesia. Okay, it's not the laxatives that they gave. It was milk from cows that were in the region of magnesia. So he's using a play on words. It's not literally given milk of magnesia. It was milk from magnesia. Okay. All right. So when you read through that, don't go bragging to your family that you know something about. That's not where we get milk of magnesia. He's just being a goofer. All right. So let's see. All right, so the minimum unit, just switching back to electricity for a second, the minimum unit of electricity would be the electricity in one electron, okay? You got one electron, you've got one tiny piece of electricity. With magnetism, though, you've got something a little bit different. Magnetism, you can create a minimum quantity of magnetism. And so charged particle in motion creates a magnetic field. And we talked about the atomic structure, and the atoms are always moving because the electrons are just blasting around the nucleus of the atom, right? So what is an electron? Charged particle, and it's in motion, right? So the minimum amount of magnetism that can be created would be the magnetism off of that one electron. Okay, that's what we refer to as electron spin. And but here's the rub, is that if you've got an electron, and we're going to draw an electron as kind of a square instead of round thing. If we've got an electron, then what we've got in our magnetic field is we've got our magnetic field goes in one end and out the other, okay? So we have a north pole and we have a south pole. It's just a perspective thing. Somebody put north and south on it, and that's what we went with. So the magnetism comes out of the south pole and goes into the north pole, okay? So magnetism is strongest closest to the magnet. I brought some magnets. I'm only going to do this one, so I only have to pick up one. So it's a magnet. Right? Why didn't it pull into the wall? It's not close enough, exactly. So the magnetism is strongest closest to the magnet. Grab another one so I don't have to bend down. So is there magnetic pull between the magnet and the dry erase board? Yes, there is. Is there if I pull it out here?
No.
Yes, there is. It's extremely weak and it's undetectable. If I took it all the way over to White's administrative building, a quarter mile that way, is there still a magnetic field that's reaching from this thing all the way over here? Answer is yeah. So the minimum the minimum amount that you can create is what comes off of a single electron, but the minimum unit of magnetism doesn't exist. You can take this thing all the way across the globe, and theoretically, you've got magnetism that's reaching from this tiny magnet all the way to this little classroom, right? So it's weak. It's so weak that we can't detect it, but the further out we go, let's see if I can do this. Right up next to the magnet, you've got a big, fat, strong magnetic field, okay? And then right off of that, you can tell how that's smaller, right? I'm a genius. And then after that, it gets weaker and weaker and so forth. So you're gonna have a question on test. What's the minimum unit of magnetism that can be created? Off of one electron. What's the minimum unit of magnetism? You said none. There is none. No minimum unit of magnetism because those magnetic field lines reach out indefinitely. Okay, you see the difference between the two? You can create a minimum unit, but that minimum unit is then going to create a magnetic field that reaches out indefinitely, and this out here is going to be so weak that you can't detect it. So no minimum unit of magnetism. The minimum that can be created would be off of a single electron in that electron spin.
So would you say it's infinite or
Infinite.
doesn't it exist?
Yeah, well, it's infinite, yeah. They're really kind of either way, yeah. So they reach out infinitely, and therefore it doesn't exist, right? Okay, everybody good with that? Okay. Then, okay, so again, just basic information. You put a lot of them together and you create a magnet, and a magnet can then do something, right? You put enough of the magnetic moments together, and what you can get is what we refer to as a magnetic domain. So we'll build up enough magnetic domains, and we've truly got a magnet, right? So this, by the way, this is it's a permanent magnet. It's created. I'm not going to be able to make this magnet lose its magnetism, but it's man-made. Almost every magnet that you run into that you'll see is man-made magnet. So they take nickel, cobalt, steel, iron, something, and they kind of combine the things together and create a permanent magnet that's man-made, and they tend to be much stronger than natural magnets. Natural magnets are really, really pretty weak. Okay, even the magnetic field of the Earth is very, very weak compared to what we can create. All right, so magnets have two poles, and that's what we refer to as dipolar. You know, north and south pole. All right, so those are all permanent magnets, natural magnets, weaker than man-made magnets. Make sure I don't miss anything. All right, so different types of materials behave differently in a magnetic field. So basically we have four. Okay, so what we have, just going from top to the bottom, is we've got non-magnetic. So a material that's non-magnetic has, you know, the magnetic field has no effect on it at all. So it doesn't attract, doesn't repel. There's just no effect on it at all. So I think wood was used as an example. And then we've got diamagnetic. And a diamagnetic material it has a weak repulsion. Okay, so it actually repels magnetism, but it's so weak that you can't really tell it. Like if I were to drop water as an example, if I were to drop this in water, it wouldn't spit it back out, right? It wouldn't even float. It'd sink right to the bottom. You couldn't tell that there's a repulsion there. It's not, you know, it's not like Moses crossing, you know, the Red Sea, whatever. You know, it's not going to part the waters, right? It's just going to drop to the bottom, and you're not going to be able to tell anything, right? So that would be a diamagnetic material. Ferromagnetic material is what you're most familiar with, and a ferromagnetic material is something that's strongly attracted. Now you can stick the magnet to it. So again, iron, cobalt, nickel, things like that, but especially iron. Then we've got what we refer to as paramagnetic material, and paramagnetic material is weakly attracted. And it's stuff that you wouldn't really expect to be attracted. Like, I think this is aluminum. So I stick this to the bottom of this. This is aluminum. And I let go, and what happens to it? Now I've got two magnets to pick up, right? Kick that one out of the way so I don't slip on it. So how do we know that it's, you know, weakly attracted? I've actually seen it. So I was a student once, right? And you like to think you're always a student, but I was, you know, in the program once, and we did our first tour through MRI. And a guy named Fred Bussell used to be the guy who trained everybody in East Texas on MRI. I don't know where he is now, but at any rate, Fred had this piece of aluminum that was about the size of a textbook. He was telling us about the MRI, and he took a pair of scissors, and he put tape on a pair of scissors, it's silk tape, so it was real strong. He'd walk towards a magnet, and you'd see the scissors that were, you know, had a quantity of iron in it. It'd stand up straight, he'd walk away, and the scissors would drop. And then he took this big chunk of metal, and he said, he was describing the magnetic field through the magnet. He said the magnetic field is so strong coming through the magnet that it will affect the aluminum. So he took this thing and he set it right in the gantry. The gantry, you know, being the opening, the bore of the magnet, and there was nothing there, right? No pillows or anything like that. And so he's got this big chunk of metal and he stands it on end in the bore of the magnet. And it's just standing there. He's talking to us and he just reaches up and pops it like that. What happened?
It fell.
It fell, right. It fell, it made a, you know, smacking sound. This is a chunk of aluminum and it's about to fall on plastic. And I'm like, this is gonna be loud. That thing, it fell and it took it maybe 5 seconds to fall. It looked like an optical illusion. Okay, so aluminum has magnetism has an effect on aluminum, but it's got to be a really, really strong magnetic field in order to witness it, in order to see it. But there is, you know, an attraction there. Now, it wasn't such an attraction that you couldn't just reach over and pick up the, you know, big piece of aluminum. It didn't hold it down or anything like that, but there was an effect on it. It was really, really pretty wild to see. Because, I've always thought that there was no effect on aluminum until that day. Okay, so 4 types. We got non-magnetic, non-magnetic, no effect, dimagnetic, weak repulsion, ferromagnetic, strong attraction, and then you've got paramagnetic, that has a very weak attraction. All right. So electric ground, we talked about. We talked about the net electric charge of the universe being neutral, electrostatic force. That's not where I want to be. Oh, that's it. Okay, any questions on all that? The review is literally going to take longer than a lecture. Wow. Okay. So then really the only things that we have left to talk about is how we measure magnetic fields. So measurement of magnetic field would be in Tesla. Okay, so you can calculate Gauss, so 1 Tesla is like 10,000 Gauss or something like that. But if you talk to somebody about MRI and you ask them how strong a magnet is, they're going to tell you, 2, 3, 4 Tesla. Okay, so it's just a word you need to file away. But the magnetic laws. So ferromagnetic material can be made magnetic through what we refer to as induction. I'm going to tie all this stuff together here in a bit. Electricity, magnetism, and where we use it. So induction, if I have a magnet has a north and south end, and we've got the magnetic field reaching out like that. Okay? So if I have a piece of ferromagnetic material, since this is blue, we're going to say this is cobalt. I've got that out there. Okay, is it having an effect? Is the magnetic field having an effect on that piece of ferromagnetic material? Yeah, it is. It's weak. It's weak, but it's there, right? So if I were to take a piece of iron, so this is some kind of green rusty iron, and I put it right up next to this other piece of ferromagnetic material, what's going to happen to it? Well, this is being attracted by that, so is this attracting that? The answer is yeah, it is, but is it attracting it enough for it to stick to it? The answer is no, it's not. But if I were to move this, and we'll just make it all iron, just to make it simple. If I were to move the iron way over here, then what happens to my magnetic field lines? What happens to the iron?
It's in the Bushong.
What's that?
It's within the strong field.
Is the board now magnetic? Answer is yeah, it is. Is the iron now magnetic? Answer is yeah. So that's through a process we refer to as induction. So induction is you put something close enough to a magnetic field, and those magnetic field lines will now include that, right? So 2 ways to get a bigger, stronger magnet. One is to put something ferromagnetic inside of the magnetic field lines to distort those magnetic field lines. And now our magnetic field lines go out here. Okay? So this becomes magnetic through induction. So ferromagnetic material, the main property in this context of ferromagnetic material is that it will draw in and concentrate magnetic field lines through induction. Okay? So ferromagnetic material can be made magnetic through induction. Now this is the other way that you can have a temporary magnet. If I were to move that back over here, am I still, if I move it far enough away, is it magnetic enough that it's, can do any kind of magnetic work? Answer is no. Okay, most of the time that we're talking about temporary magnet, that, it became temporarily magnetic, but when I'm talking about temporary magnets, what am I talking about? Flip on a switch, electrons travel through a wire, the wire with the electrons puts off magnetic field, it becomes magnetic, right? Turn off the switch and where's magnetism go? In a way, or in a word? Away, thank you. Yeah. Oh, when I give it away like that. All right, so ferromagnetic material can be magnetic, be made magnetic by putting it close enough to a magnetic field where the magnetic field is induced in the ferromagnetic material. So the second law of magnetism should sound really familiar to you. Magnetic force is proportional to the pole strengths. Pole strengths being the number of magnetic domains you have. Okay? And inversely proportional to the square of the distance between them. So this is Coulomb's law, is all this is. This is Coulomb's law applied to magnetism. The more you have, the more you have. But if you separate them real far, you take two magnets, and you got one magnet, how much magnetism do you have? One magnet's worth. You have two magnets, how much magnetism do you have? Two magnets worth. I take the two magnets though, and put them way out here, and what happens? Now I have four magnets to pick up, right? They're still the same strength of magnet, it's just that they're so far away that they don't really have that much of an effect on each other. Okay, so why does all this matter? Well, I'm glad you asked. All right, so what's the first thing that the electricity gets to in the system, kind of, sort of? Huh?
The transformer?
Yeah, what kind of transformer? Well, it has one coil. Auto transformer. It's a type of rheostat. It's a type of rheostat. What's a rheostat? We can turn the energy up and down, right? So we've got plugs on the primary side, and then we've got plugs on the secondary side. If I spread the plugs out, then I can affect a change that's different from if I squeeze them in together. If I spread them out, I can make a change, increase my voltage. If I squeeze them together, I decrease my voltage. I'm going to supply this with alternating current. What is alternating current? It's current that comes and goes. All right, so it travels in a sine wave like that, and it comes in and it goes out, and it comes in and it goes out. So we have electrons going back and forth. Anytime we have electrons going through a circuit, charged particle in motion creates heat, and it also creates magnetism. Exactly. So magnetism is going to be reaching out in both directions, right? So it comes out of that, and it goes into another thing that has one loop of wire, it looks like that, and another one that's real squiggly, like that, right? So now I've still got alternating current coming in and out, and I'm also going to put inside of these a ferromagnetic core, and we'll talk about that next week, or on Friday rather. I'm going to put a ferromagnetic core in both of those. So I've got alternating current, which means I still have moving electrons. And what do I create? A heat and magnetic field, right? So I create a magnetic field. Magnetic field's going to be changing because my electrons are going back and forth, and we'll dial that in sharper on Friday. Now, if I move a secondary coil with an iron core in close enough to it, I can take my electricity with my change in electricity, creating my magnetic field, and if I move this in, I can induce a magnetic field in this other coil. Okay? So as I induce that magnetic field, what I'm going to get on the secondary side is also alternating current. It's just going to increase because I've got more coils on the secondary side of my high voltage transformer compared to the primary side. My voltage goes from maybe 100 volts to 100,000 volts. Okay, remember talking about all this? Now, what can I create? I can create X-ray, do a chest X-ray, right? So then it comes out of that and it goes into filament. There is another thing, we're actually going to put our semiconductors over here. I'll talk about that later in the semester. We don't want, We don't want alternating current once we get here, and we'll talk about why later on, but I can send the electrons across the tube with very high potential, right? So that I get very high kinetic energy, so that I can create high energy X-ray photons. At the same time, we've got another circuit that comes off, and it's going to go through a MA selector, which is really just another type of rheostat, right? As an MA selector, and then it goes into the exact opposite of this. If this is a high voltage transformer, it steps up voltage, then this is going to have a lot of squiggles on the front side, the primary side, and fewer squiggles on the secondary side. If this took voltage and sent it up, this is going to take voltage and make it go
down.
yeah. And that is through, what's the word? Induction, right. So induction. So then it comes out and it goes into the filament to create our thermionic emissions. Okay? So electricity creates magnetism to adjust our voltage so that we can use electricity to create magnetism so that we can get very high voltage so that we can manipulate relatively low voltage into extremely high voltage and create X-rays. That'll actually be beneficial. Okay? So that's kind of the wrap up for electricity and magnetism in the intro for electromagnetism. So Friday, we're going to spend the entire class period talking about this in the circuit and how we can calculate exactly how much of a change we can make here and there and down here, and why we have to have all this, and what that the cores, the purpose for the cores really are. Purpose, we can do all of this without the iron cores. I just thought I'd throw that in there. Okay, any questions?
Do we have to know parallel and series circuits for the test?
No. Okay, I'm glad you brought that up. So we used to have to calculate Ohm's law through series and parallel circuits. They took that off the registry. Just know the definitions, right? So if the electricity has to go through this to get to this to get to this, that would be a series circuit, right? But does this depend after, really this point right here, does this depend on whether or not that works? The answer is no. So these two are parallel, whereas all of that is series. This is a series as well.